Welcome, everybody. Thank you. We're going to start recording.
Yeah.
I didn't hear it, but okay.
Okay.
All
Yep,
right.
you're recording.
There we
Yeah,
go.
that was
All right. So everyone remember that we're being recorded. Welcome all. Do we have any new members here tonight that would introduce yourselves? Bill, there you go.
Hi, I'm Bill. I'm new. It's my first time.
Very cool.
Welcome.
How'd you find out about us?
My girlfriend and her sister got me this for a Christmas present.
Ah,
The
awesome.
cat?
Yes. No, I've had the
Well,
cat.
very good. Well, welcome in. Good night. Good night to start. Probably have a pretty decent lecture from Tim. Excuse me. Anybody else new tonight?
I'm new.
Andy.
Hi, Andy.
I joined. I'd been wanting to join for a while and just never did. And then finally did.
Good.
Welcome, Andy. You all can visit us at Garvey Ranch any Wednesday night and keeping track. We have, as spring and summer comes around, we have a lot more of events happening.
Nice. Yeah, definitely looking forward to that as the weather improves.
Yeah, no, tonight's not the night to plan going out. Yeah.
And
Yeah.
the rest of
Well-
this week, more or less.
Yeah.
Good. Anybody else?
So,
Thank
Andy,
you, guys.
do you know anything about David or Keith? I mean, you guys seem to be in the same sort of industry.
No. I mean, well, I work in visual effects, so I get to be. I'm not a scientist. I'm a science enthusiast.
Right.
So
I think
I
they were
work-
talking about your guitar playing. Your
Yeah,
guitar
I'm looking
playing.
at the guitar here. Yeah.
Yeah,
we're going after the guitar.
yeah. It lives in my lap while I'm doing the rest of my work.
Okay, do we have any other new members? Nope. Okay. Well, one of the things we need to do tonight is install the new board members that were voted in. Spencer, you want to take care of that? I think you have all those numbers and information, I believe.
Well, I don't have
Somebody has it, I hope.
the numbers, but I think the board members. Why don't we just introduce ourselves? So,
Okay.
Daryl.
I was reelected. I'm Daryl. I am the president. And I can introduce everyone, I guess.
I was
Spencer's our-
reelected for some strange reason. I'm just a member of the board, just the guy who sits
Mhm.
around, and makes rude noises during the meeting.
Spencer's our secretary, and the board members that I see here are Joe Phipps and Dave Yackerson, and who else? Greg Thomas, bunch of names. Who else
Greg
is
Thompson.
Greg Thompson,
Tim and Greg Thompson, two
Tim and Greg
Thompsons. on the
Thompson. Is
board.
there any other board members? Alicia's here. I see Alicia just came in, so she's a board member as well. There she is.
Alicia's our
Reelected
vice
Alicia.
president.
She
Yeah.
is.
That's right.
Let's see, anybody else?
John's not here. He's our treasurer.
Don't see John.
Curtis, not here. I haven't seen him.
Raphael's not in yet.
And yeah, Raphael is usually here, but he's not. And I think that's everyone. I don't have the list in front of me, but that's okay. So new members, new elected officials and board members. Welcome to the new year of LEAS. Yay for all of us. Let's have another good. Last year was very good. Let's have another really good year. I see no reason why we shouldn't.
Just keep the club afloat. I can't tread water.
No problem. Okay. Updates. I don't know what should we have to update this month, because most of our activities are shut down. Mount Wilson is probably full of snow at the moment.
You think?
Lockwood's been a little too cold as well. Garvey's open every Wednesday.
Isn't there snow up at
Except on Wednesdays like today.
Right, something was like that. And Ford as well is up in snow country. So
Isn't Lockwood snowed in?
No,
I
but
didn't look
there's about 2 to 3 inches of rain on the ground right now.
ooh,
Oh,
is it supposed to get cold enough
The
tonight?
snow
for
level, snow level right now is very high. It's like 8,000 feet. So everybody's getting lots and lots of rain.
Okay.
Yeah. My ex lives at Pine Mountain Club and they're just getting nothing but rain. It's any snow they had accrue has been kind of washed away by the rain.
Maybe tomorrow night.
Okay. We don't have any Mount Wilson announcements. We don't have Lockwood announcements. Garvey Ranch is still the best place for new members to go, old members to go, for help with your telescopes, and to just hang out and have a cup of coffee made by Keith.
Or
One of-
soda pops or
Evan.
water.
One of our two baristas that are there almost every Wednesday. Keith is also in charge of the loaner program for new members. If you want to borrow a telescope from LAAS, and show up at Garvey and talk to Keith and he'll set you up.
Yep, I got the best job in the club.
Cappuccino.
Very cool. Do you have any Dobsonians?
2.
You have 2?
Mhm.
Okay.
One's a 10-inch, right?
No, they're both 6s.
Oh, really? What happened to the 10-inch? I donated that I think I donated both of mine to the club at one point.
I have not seen. I've only seen since I've been doing it. There's only been 2 6s, and that's it.
Some
mean,
guy,
somebody-
One of them came from Spencer, and one of them was there that predated me.
yeah.
Yeah,
And-
that would have been me.
And one of the 10 inchers, somebody loaned, checked it out, never returned it. And
Yeah,
and
I
left
heard
town.
about that too,
Still on loan, I guess.
so to speak.
Hey, Jack, how you doing, man? Nice to see you.
Wait a minute, where?
Hey,
is he? Oh, there he is.
Hey, everybody.
Well, the committee reports are kind of the same thing as the updates for each of our properties. So unless anybody has anything that they need to talk about or bring up, we can actually start our talk right away, because I'm expecting to get I'm expecting a lot of Q&A at the end. So unless anybody needs to hear anything else, let's go to that.
Don't forget January 28th. Don't forget about January 28th. Griffith is open.
Griffith is going to be our first, actually it's our second wide open, no restriction star party. at
First one of the
Griffith.
year, though.
I'm sorry?
First one of this year.
First one of this year, that's true. So we're
Also,
back, we are back so far to normal star parties at Griffith once a month, so look for those.
Daryl just received 2 outreaches from Evan.
Yes,
There's two elementary school outreaches from Evan. One is at Arroyo Vista Elementary School on the 19th of January on a Thursday. And the other one is going to be at Annandale Elementary School on the 27th. So you have to call them, let them know you're going to show up.
okay. Yeah, and also new members, if you're interested in outreach, contact, I think his email's
Evan
and he's in charge of the outreach, and if you want to do that, contact him. We'll find out what, kind of telescope you have, a little bit what you know, and then be put on the contact list for the outreach, and you'll find out when they are. And go help out, show the kids. Anything else? Tim, you ready?
I guess I am. Let me see if I can properly share my screen here. Let's do that. And then
One second, Tim, while you're getting ready there, for the new members. Tim is a longtime member, been president multiple times, retired physicist and astronomer from JPL. Sounds like he's done a lot of fun things. Worked in the radio astronomy group at JPL, looking at planet atmospheres and magnetospheres, including radio observations with the Deep Space Network, which is pretty big. Bunch of years on Astro Project and a lot of other fun things. Mount Wilson all over the place, docent, session director, on the board. If you want to know something, probably you just ask Tim. He'll probably know. Okay. Okay, Tim, thanks. What is gravity? Uh-oh. Did we lose Tim?
Well, once he started sharing, his audio degraded severely.
Oh,
He's
really?
frozen. He's frozen now.
Yeah.
That's probably my fault. I shouldn't have stopped him.
Yeah, we'll
Well-
blame you, Daryl.
Well, he'll just restart and come back in.
He's back. He's back.
He's back. There he is already. Okay.
Your audio's muted, Tim. That's
You're
what,
mute.
your audio is muted.
Can't hear you yet.
Tim, your audio is muted.
Spencer, can you unmute him?
There,
There you go.
able to hear me now.
Yes.
Yes.
I have an unstable internet connection. It's raining cats and dogs, and my cell phone beeped, and I'm under flash flood warning. I'm 2.5 stories up, so if you see me wash away in the flood, you know the world is coming to an end. So just put on your football helmets and get ready. So hopefully this will stay up for a little while. So the title of my talk is What is Gravity Really? And in the end, I'm going to tell you what gravity really is, but I'm actually going to start with something that seems completely out of place. And you will think, now let me see if I can do this. There we go.
Hey, Tim,
You
might
might
want
think that starting with Zeno's paradox is the wrong way to talk about gravity. Yeah. I might, what?
kill your video. That'll give you a little more bandwidth.
Yeah, that's a possibility. So how do I don't know how to do it? There we go. I'll just do that. There. Hopefully you can still hear me anyway.
Mm-hmm.
And so starting with Zeno's paradox may seem kind of weird, but things that are falling under gravity are things that move, and motion, believe it or not, is probably one of the biggest pain in the neck problems that scientists and philosophers have had to deal with for thousands of years, and it's still incredibly hard to deal with and understand. And so Zeno is one of these guys who took the extreme position of deciding, based on his intellect, that all motion is completely illusory. Nothing ever actually moves. It's all just a big fake. And it's usually told in the parable of Achilles chasing the tortoise, which you see here on the lower left. You give the tortoise a head start because the poor thing, Achilles will just stomp on it and run off. But Achilles always has to get to where the tortoise used to be because the tortoise is still moving. And there's an infinite succession of steps trying to get to where the tortoise used to be. And in Zeno's mind, that takes an infinite amount of time and must be impossible. And if you fire an arrow, like we see in the upper diagram, first has to cover half the distance, then it has to cover half that distance and half that distance, and so on ad infinitum, literally, which again in Zeno's mind takes an infinite amount of time. So he decided it's all impossible. And Diogenes, who's famous for wandering around Venice with his lamp looking for one honest man that he probably didn't find, answered Zeno by not saying anything and just getting up and walking around the room and sitting down again and saying, well, there you are, I'm moving. And Zeno didn't really buy that argument. So if we go now, of course, today we know that you can sum an infinite series to a finite limit, and mathematics has defeated Zeno's paradox, and nobody really cares about it all that much anymore. But about 100 years later, Aristotle had a different and more practical problem with motion. He divided motion into two concepts: natural motion, which is falling under gravity, and forced motion, which is pushing something. So he figured once an arrow leaves the bow, it should simply stop in midair and fall to the ground because nothing's pushing it anymore. The string is not there. Once it leaves the string, nothing's pushing it, it should fall. He didn't understand why it didn't. So he made up a reason. The arrow, as it moves forward, occupies volume that used to be occupied by air. So there's a little vacuum behind it, and the air rushes in behind, hits the back end of the arrow and pushes it along, and that's why the arrow keeps flying. We now know that's a perpetual motion scheme that won't work. But of course, there's no reason why Aristotle would know that. And so I start with Zeno and Aristotle just to remind you that motion, just motion by itself, can be a problem if you don't have lots of modern science and the like to back you up. So I'm going to fast forward a couple of thousand years, and just trust me, during those couple of thousand years, philosophers and scientists are still arguing about motion, and we'll see more arguments about it in a few minutes. To Galileo. Now, first thing I want to say about Galileo is that he gets credit sometimes for inventing the telescope, but he didn't. Hans Lippershey, a Dutch eyeglass maker, invented the telescope. Galileo also gets credit for being the first person to do astronomy with a telescope. That is also not correct. Thomas Harriot, pictured here, was the first. His drawings and observations predate Galileo by several months, but Harriot was kind of a dilettante. He looked through the telescope, saw a few things, said, yeah, I saw some stuff, and then went on to do other things. While Galileo carried out a consistent, constant program of astronomy. He paid a lot more attention to what he was looking at, discovered the moons of Jupiter, discovered mountains on the moon of the Earth, discovered the phases of Venus, and so on. Discovered all those things because he actually paid attention to what he was doing when Harriot didn't. So I just want to get that out of the way. But what we're really interested in when it comes to Galileo is two things. First, Galileo was the first scientist, philosopher, to give us a theory of relativity. And that means if two observers are moving relative to each other, they will see things a little bit differently, but they can compare notes. And if they have the little equations that describe how their observations are tied together, then they can agree that they both saw the same thing in the same way. The difference was caused by their motion, not because of something more fundamental. And it's very simple. It's the addition of velocities that you're used to. It's the old story you've probably heard. If the train goes by at 30 miles an hour and a guy throws a ball at 60 miles an hour, somebody on the ground says it was going 90. Somebody on the train says it was going 60. They stare at each other. You're both nuts. And then they compare notes using the equation. Oh, we saw the same thing. It's cool. He also, according to the story at least, dropped a couple of heavy things from the Leaning Tower of Pisa. He probably didn't. He used an inclined plane for his experiments. But he did determine that the acceleration with which things fall is not dependent on their mass or their weight, which was and is counterintuitive. You would think that heavy things, since they're being pulled harder by gravity because they're heavier, should fall faster, but they don't. They fall at the same acceleration, which was very counterintuitive. Nobody really wanted to believe it at the time, but it's true. And it's also the observation that eventually leads Einstein to general relativity. It's a really big deal that Galileo made this observation in the mid-1600s. So we go past Galileo to Isaac, and Isaac did a couple of interesting things. First, he's the first one to codify laws of motion. Galileo was the first to give us a theory of relativity that explains how observers deal with their relativity. Added to it, laws of motion. The first one here, about everybody continues in a state of rest or uniform motion until the force acts on it, is basically the law of inertia. And it solves Aristotle's problem with the arrow. Aristotle had to come up with a way to keep that arrow moving because it should stop and fall. And Newton tells us, well, no, actually, it should just keep on going. That's the natural state of motion. And so the ancients and the moderns have a much different notion of what natural motion is. And here Newton codifies it and solves the problem. His third law, to every action, there is an equal and opposite reaction, which is a little simplistic, is what makes rockets work. For instance, you throw a bunch of junk out one end of the rocket and the other end goes flying off into space. Obviously, doing that in practice without blowing yourself to smithereens is complicated, but in principle, it's just that easy. It's Newton's third law. The one we're interested in is the one in the middle here, his second law, which tells us that the force on an object is going to be equal to its mass times its acceleration, which is more properly expressed as the first derivative with respect to time of the momentum. But F equals ma is what everybody learns. When you had your introductory physics class, and of course you all did, then that's what you learned, force equals mass times acceleration. And if you didn't have an introductory physics class, go back to school and take one, because everybody should have an introductory physics class. And Newton was the first one to codify a law of gravity. Prior to Newton, things fell. Why did they fall? Because they're supposed to fall. But Newton came up with a reason, his law of gravity, which is expressed here. The big G is a constant of proportionality that you must determine by experiment. You can't derive it from any theory. And it's probably the least precisely determined constant in all of physics because it's devilish hard to measure. But we know it to a few decimal places. And you multiply that times the two masses of the two things that are attracting each other and divide by the distance between them squared. And I use the letter R here because in every book you ever see, that's what they're going to do. It's the radial coordinate in spherical coordinates, radius R, and that's what they do. But there's something interesting about this. If you combine Newton's law of gravity with his second law of motion, and you see I've done that in this first equation, and I've rewritten the m's a little bit. The big capital M is, say, the mass of the Earth, and the little m is the mass of, say, you, especially when you jump out of a perfectly good airplane with a parachute for some strange reason and fall. Well, okay, you're falling under gravity. And this shows you why Galileo observed that the acceleration does not depend on your mass. Because if we combine Newton's law of motion with his law of gravity, you can divide out the little m, the mass, and you get the acceleration depends only on the mass of the Earth. That solves one problem. It explains what Galileo saw, but it creates other problems. For one thing, Newton was very unhappy with this equation and complained about it and mentioned it in his diaries and writing, that even things that are very far away, like the Earth and the Moon, which are controlled by this law, there's nothing connecting them. There's no rope, string, spring. There's nothing you can see. They're just out there in empty space, and yet they attract each other. How does that happen? He didn't like that action at a distance idea. We today would use a gravitational field as the reason, but of course, fields and field theory and all that were 200 years in Newton's future, and that idea would never have come to him. So he was really bothered by action at a distance, didn't like it, but he knew and insisted his equation is right. It works, nothing you can do about it, you're stuck with it. And the other problem is, why is it that inertial mass from the second law, a measurement of your resistance to acceleration, why should that be the same as the things we're calling mass in the law of gravity? And in theoretical physics, we make a very plain distinction between inertial mass and gravitational mass, and something called the principle of equivalence, which we will see later on, which tells you that they should be the same, and we'll see why and what that means for theoretical physics. But this is another big deal. Why are those two masses the same? Newton couldn't figure it out. But Newton understood that from Galilean relativity, simple, easy motion in a straight line at a constant speed, it's all relative. Anybody can call themselves at rest. Anybody can call themselves moving. But he was an advocate of an absolute reference frame called space. And he explained this by using a spinning bucket. We're going to come back to this bucket later on. But if your bucket full of water is sitting there not doing anything, the surface of the water is flat. If you spin the bucket up to a constant speed, the water gets up to the same speed as the bucket. Then once again, the bucket and the water are not moving relative to each other. In both cases, sitting still and spinning, the water and the bucket are at rest relative to each other. But Newton says the reason the surface is curved is it's not at rest with respect to absolute space. Therefore, there is some absolute reference that you can use. We're going to come back to this in a little while and find out that maybe that's not the way it works. Along comes Maxwell, and he invents the theory of electromagnetism. And a very disturbing consequence of that is that you can take the fundamental constants that are given here, vacuum magnetic permeability and the vacuum dielectric permittivity. These tell you, they measure the ability of a vacuum to support electric and magnetic fields. And you can calculate the speed of an electromagnetic wave, and light is an electromagnetic wave, from this simple equation. It's 1 over the square root of the product of those two constants, but they're constants. They're fundamental constants, which means that everybody, no matter how they're moving with respect to anybody else, will measure exactly the same values for those numbers, which means they must have exactly the same value for the speed of light. So the constancy of the speed of light is not something Einstein made up in order to make special relativity. It comes right out of classical electromagnetism as a necessary consequence. And this is a violation of Galilean relativity, which is how you compare moving observers in Newtonian physics, which means that the physics of Maxwell's electromagnetism and the physics of Isaac Newton are not compatible with each other. And this created an intolerable conflict. And it's expressed by me this way, that those three things everybody knew absolutely must be true, is that the physics of both Newton and Maxwell, there's no exceptions, they're true, there's nothing wrong, there's nothing you can do about it. Both of those theories are absolutely correct, and that's impossible. They cannot simultaneously both be correct. You can see why I call this an intolerable conflict. Something obviously has to break here. So everybody was striving to rescue both theories. If you recall the famous Michelson-Morley experiment, where they were looking for the speed of the Earth relative to the speed of light moving through this stuff they called an ether, they couldn't find it. The speed of light was a constant. They experimentally determined. So in order to rescue both of them, physicists were inventing some contraction of the experimental device that Maxwell used because of pressure from this luminiferous ether, which was the medium through which light moved. What Einstein actually did that was so incredible at the time was not to come up just with special relativity and the constancy of the speed of light, which you can already find in Maxwell. He chose sides. He actually decided that Maxwell right, Newton wrong, and that was about as heretical as you could get. And that was the really rebellious thing that he did. And I'll point out, we always teach special relativity as a theory in mechanics, how things move and how length contraction happens and time dilation happens to your clocks. But the title of the paper in which he introduced it is called On the Electrodynamics of Moving Bodies. And everybody just ignores the word electrodynamics in the title, which hides the fact that he got this from Maxwell's theory and not just made up entirely in his own mind. He did a lot of original stuff, but that bit about the speed of light being a constant was not it. So he replaced Galilean relativity with Maxwellian. Actually, Lorentz relativity is the correct way to pronounce it. And I show the equations here. And the point is, if you look at this, so you see my cursor, this thing here called gamma, which is the inverse square root of 1 minus your speed squared over the speed of light squared. If your speed is really, really small compared to the speed of light, the ratio is really, really tiny, and this becomes 1. And if it's 1, you get Galilean relativity or Newton, which means that Newtonian physics works just grand at small velocities compared to the speed of light. And you only need to worry about Einstein if you're going really, really fast, very near the speed of light. Then you need to worry about changing the equations by which moving observers compare their notes from Newton and Galileo to Einstein. So this is called special relativity because it handles the special case of a constant speed in a straight line, constant velocity in the terms of physics. But nobody had tried to address the general case. What if things are accelerating? What do you do about accelerated motion? Nobody can handle that. Einstein went after that and couldn't solve the problem, and slaved over it and strived over it, and finally hit on an idea, a really spiffy idea, which really finally, if you will, combines motion and gravity. And this idea comes from that spinning bucket Newton had, and an Austrian philosopher, mathematician, scientist named Ernst Mach. And what Mach did, the easiest way to describe it is that Newton was talking about the bucket spinning in the universe that's standing still. And so Mach decided, what if you hold the bucket still and spin the universe around the bucket? From the point of view of a physicist, that's pretty silly, but philosophers have no problem with such things. They can spin the universe in the morning before they even have their coffee. And if you do that, a little observer sitting on the bucket will see the same thing in both cases. So you can't really tell, according to Mach, that you are spinning on the bucket. You could be sitting still while the universe spins around you. Einstein took that idea and applied it to gravity and said, over here on the left, we have somebody standing there in a constant gravitational field. Over on the right, we have somebody in a rocket accelerating with exactly the same acceleration as experienced by the guy in the gravitational field. And Einstein postulated these two situations must be exactly identical. And so as long as you're not allowed to look outside the rocket, you're only allowed to do experiments in your little chamber. There is no experiment you can do that will tell you the difference between these two scenarios. This solves the problem of why Galileo saw heavy things fall with the same acceleration as light things, because it has nothing to do with a force of gravity. It has to do with being in an accelerated reference frame. There's no force. It's just that your reference frame is accelerated. So everything in that frame of reference will accelerate the same. Excuse me. And by the same logic, if you fire a beam of light, hopefully you can see my cursor. If you fire a beam of light across this cage, you might expect that beam of light to just go straight across. But if you're over here in the rocket, that beam of light is going to curve down because the rocket is accelerating as the beam of light crosses the cage. So since there's no experiment that will tell the difference, that's how you predict in a gravitational field, light will follow a curved path. And it does. We see that. We've measured that. That's what Eddington famously observed in 1919 with the solar eclipse. And this bolsters the principle of equivalence. But meanwhile, a German mathematician named Minkowski had turned special relativity into geometry. And when Einstein saw this originally, he thought, that's cute, geometry, who cares? But when he started working with the principle of equivalence, he realized, especially when he saw the curved paths for light, you can express his theory geometrically. So he went back to the geometry thing. This, what you see here, is a demonstration of Minkowski's geometry of special relativity of space-time, which is purely Euclidean. So the little equation in the upper side, upper right, is a metric for ordinary Euclidean geometry, and the two equations in the bottom center are the equations that describe the metric for the geometry of special relativistic space-time. And you can write it either way, with the negative signs or with the positive signs, as long as the signs are consistent and you treat it consistently throughout your calculations, it'll work out fine. So I want to just explain a little bit about the terminology, because it becomes important when we talk about the geometry of space-time. A metric in mathematics is a function that defines the distance between the elements of a set. And we're talking about a mathematical distance, not necessarily a physical distance. That metric tells you what mathematicians define as the distance between the elements for that set. If you have a set with a metric, then in the terminology of mathematics, that's a metric space. Physical space-time and relativity is a metric space in the terminology of mathematics. And so is Newtonian space. So we have all the math and the physics come together. Now, I stole these two slides, that one and this one, from my talk on black holes, because I was working on this talk until, a couple hours ago or something, and finally decided to give up, that I've done the best I can for the time being. The equations you see here describe the metric for general relativity, and you're not supposed to make sense out of them because you really need to know a lot of math and physics to do that. Don't worry about it. What you can tell is that it's complicated, and that's really what you need to know. The top equation describes the metric for space-time outside of a non-rotating black hole. Spin the black hole, and it takes 47 years for us to try to figure out what the math looks like for that metric, and that's what's at the bottom with all kinds of little equations to go along with it. It's a pain in the neck, but it shows you what the geometry mathematically looks like. And here's a picture of what the geometry conceptually looks like. The image in the upper left is the one you usually see with the balls digging little gravitational wells in a sheet. it's an analogy. Space is three-dimensional and space-time is four-dimensional. And so the diagram here on the lower right, the big one, is probably more realistic, trying to depict how space curves in three dimensions, the geometry of space-time. So this means that gravity is no longer a force. It's just an expression of the geometry in space-time. Anything in free fall is simply moving along a geodesic path in space-time. And the geodesic is a path that minimizes the distance between points. So many years ago, when I flew from Los Angeles to Switzerland nonstop, I wound up flying over Iceland. And likewise, coming back from Switzerland, the frozen over North Atlantic because it was winter. And if you've flown anywhere, if you're used to flying, you know that your flight follows one of these great circle routes around the Earth. And that's what a geodesic is, except the shape of space-time, its geometry is rather more complicated than the Earth. So a geodesic path can be a lot more complicated. So in classical physics, if you look at general relativity in its native language and accept it for what it is, there is literally no such thing as the force of gravity. It's all just an expression of geometry. You can model gravity as a gravitational field. That makes it a little easier to work with, especially if you're navigating spacecraft around the solar system and you need to make general relativistic corrections. You can model it as a field, use gravitational field theory, and everything will work. And that pretends that gravity is a force in classical physics, but it really isn't. And the fact that it really isn't raises another really nasty problem. And that is that we now accept quantum physics as the defining physics, the fundamental physics of the universe. And here I'm showing you a table of 17 particles. There's actually more, but these are the fundamental particles in the standard model of particle physics, which unifies three of the classical four fundamental forces. There's electromagnetism, and then there are two nuclear forces, the strong force and the weak force. The strong force is responsible for holding nuclei together, and the weak force is responsible for radioactive decay of heavy nuclei, but it does not include gravity. The way all this works in something called quantum field theory is that you see 17 particles here. So the entire universe is filled up with 17 fields, one for each one of these particles, and the field exists everywhere. But when you observe a particle like an electron somewhere, what you're seeing is a local concentration in that field. And that's the mechanism by which quantum field theory works. And space-time is the background that these 17 fields are imposed upon. The problem is that gravity is the space-time background, and you don't know how to handle it because every one of these particles, because it has mass, will perturb space-time. It'll be a tiny perturbation, but it will do it. But you don't know where the particle is till you look at it, which means you don't know where the disturbance in space-time is before you look at it. And everything falls into a nightmarish mess and you can't understand it at all. So there is no quantum physical theory of gravity at this time. So the thrust of modern theoretical physics is to find one. Now, of course, it's possible that no such theory exists, and maybe we're just barking up the wrong tree. But quantum field theory is amazingly successful at handling complicated problems in theoretical physics, and we are not prepared to throw it out. So we're looking for a way to create a quantum theory of gravity. And there are two big leading candidates. One of them is something called loop quantum gravity, which is kind of the sledgehammer approach. We're just going to quantize space-time itself, turn space-time into another quantum field. And it's done using a network of finite, obviously incredibly tiny loops woven into the factor of space and gives you a minimum length called the Planck length of 10 to the minus 35 meters, and a minimum time called the Planck time, which is like 10 to the minus 45 seconds, ridiculously tiny. And both space and time are quantized at that scale, time and space, so that intervals of time less than the Planck time, intervals of space less than a Planck length are meaningless. They don't exist because that's the level at which they're quantized. Now we know that general relativity is the low energy limit for loop quantum gravity because we made it that way. It's deliberately designed to have that feature, and we need it because general relativity is what we see when we look at the universe, and we need to recreate what we see. The other, commonly just called string theory, is really correctly called supersymmetric string theory because it requires a property called supersymmetry. It keeps space-time background as it is and remodels the particles as little stringy things instead of little points. And the stringy things can be closed loops, kind of like the loops you see in loop quantum gravity, or they can be little segments of strings wiggling around at the ends. And they reside, unfortunately, in a space-time that requires 9 or 10 spatial dimensions, depending on which theory you prefer. 10, I think, is correct for M theory as invented by Ed Witten. But we only have 3 spatial dimensions, so we have to find a way to get rid of 7 of them so we don't notice them in our everyday physics. That's a neat mathematical trick, but you can do it. You can compactify the dimensions and hide them from your view, but they're still there. And there are ways to try to go looking for them with high energy particle experiments or even little torsion balance experiments in a lab. These 2 theories are really the leading candidates. Neither one of them is complete. Neither one of them does all the things you want them to do. In particular, calculating the masses of the fundamental particles doesn't work for either one of them. And string theory, because it requires supersymmetry, requires a whole bunch of new particles to worry about that people are looking for and haven't found. So they're both kind of shot in the dark efforts to try to find a way to create a quantum theory of gravity. The really interesting thing about string theory is that it was invented strictly as a quantum particle theory to explain particles bouncing off each other. It didn't work. They got rid of it. But people at Caltech playing around with it, Schwartz and Shirk, suddenly and surprisingly realized when they looked at it at low energy that its low energy limit is general relativity. Exactly, not approximately, but exactly. And there's no good reason why that should be true because the theory did not have general relativity anywhere near it when it was invented. unlike loop quantum gravity, which does. This one didn't. So it was very exciting, and a lot of physicists piled on and thought, we're on to something, we found something, and then nothing happened, and now they're getting bored again and looking for other things to do because they're not really making much progress. So this is the status that we find ourselves in now. We're looking for a quantum mechanical theory of gravity. Theoretical physicists are convinced that general relativity is incomplete because it doesn't have a quantum physical analog. So if we go back to our original question, what is gravity really? I'm going to give you what I think is the absolutely unchallengeable, indelible, correct answer to that question, which is something you've probably heard around the office when you're at work. And that is, we'll get back to you on that because we're still working on the quantum theory. Classically, it's geometry and gravity is not a force. That doesn't work with quantum mechanics. So we have to figure out something to do about it and hope from, and it's a little shorter than most of my regular talks. And who knows, maybe I'll make it longer if I work on it a little more. But there you are. I'm done. Thank you. I appreciate it. I hope you're not all bored.
No, fantastic, Tim. Thank you. I'm looking through the chat and I see an interesting question from Pablo Lewin. It says, Tim, if nothing can go faster than the speed of light within space, but the universe is expanding faster than the speed of light, what's the name of the medium that contains the expanding universe, which allows it to expand faster than the speed of light? I didn't know that it was. Is it actually?
Okay, yes. The expansion, I think anything with a redshift greater than 1 is technically moving away from us faster than the speed of light. The first answer to that is that nothing can move, indeed, faster than the speed of light through space, but space itself can move with whatever velocity it wants to move, 10 billion times the speed of light, fine, dandy, no problem. So what we're seeing is space stretching and carrying the stuff along with it. So it looks to us as though it's moving away faster than the speed of light, but it really isn't because it's not moving through space. It's being moved by space. The other thing is more subtle, and that is the use of the word expansion to describe the dynamics of the universe. Everybody talks about an expanding universe. That's misleading, but unfortunately, it's the best we can do the English language. If you've ever tried, translating or interpreting from one language to another, you've probably run into the problem that there's really no one-to-one correspondence in dictionary words from one language to another. You have to interpret phrases and interpret meanings, and there's a cultural basis to the language, and it often happens that there's simply no good way to translate a sentiment from one language into a sentiment in the other language. It's really hard. I've tried that kind of thing myself. I've studied a few languages, and it's really a monster. The native language of theoretical physics is mathematics, and it is devilish hard to translate and interpret the mathematics into any human language like English.
Can I clarify my question a little
Yeah.
bit? What's at the edge of the expansion? In other words, the universe is expanding. It's going to be expanding within some
Yeah,
sort of...
I'm actually getting to that.
Oh, okay.
There is no edge. There literally is no edge. The universe is not expanding into anything. Expansion is the only English word we can use to describe the fact that in the geometry of the universe, the scale factor, which describes the curvature, is changing in a way that mimics what we would see as normal expansion. But the universe is not expanding into anything. It cannot be expanding into anything in normal physics, simply because the universe is everything. And if you have everything, the moment you talk about it expanding into something else, you're talking about outside everything, which doesn't work. You can get around that with a multiverse cosmology, but then you're going to wind up with the same problem. Is it infinite? Is it finite? Does it have boundaries? But in classical expanding universe cosmology, that's really the best that we can say. Is it is definitely not expanding into anything. It's just that mimic of expansion in the mathematics, and we try to translate that into English, and it really doesn't work, but that's the best we can do. Okay.
Okay, we're open for questions.
I have one.
Yeah.
Yeah. So in the notion of an expanding universe, does that mean that, I mean, I'm assuming that means all of the particles that make us up are all moving apart from each other as well? And would that mean that like we're like everything is actually just kind of getting larger in that way? I was always wondering how that motion worked out. I mean, it's not literally just you know?
Yeah, there I'm trying.
Like I'm assuming every particle
zooming in.
Let him catch up.
Yeah. Gravity opposes the expansion. So gravitationally bound structures do not expand with the rest of the universe. So a galaxy, for instance, or the local group of galaxies, probably, like our local group, will not expand and is not expanding. The rest of the galaxy clusters and groups are expanding away from us. There will come a time when the entire universe consists only of our local group of galaxies and nothing else. And unless people have some record from the past of millions of years ago when they used to be able to see galaxies that are gone, nobody will know that the universe was ever anything except the local group of galaxies.
And that's because the stars that we see, or I should say the galaxies that we see that are far away.
That's right.
The word motion is so deceptive here, Tim. This is Greg. We say like, well, this galaxy is moving away from us. That's not really correct, right? We measure a speed at which it's moving, but really the distance between us is changing, or that galaxy is being moved because of the expansion. Yeah.
It's sort of deceptive, like the expansion thing, in that everywhere you go in the universe, you're going to see the universe expanding away from you, wherever you go. And so there is a relative motion, but of course, for very distant galaxies, that is not a relative motion through space. It's a relative motion of space. And then, right, you have to decide, what do you mean by moving? Do you mean moving with space or through space? And not the same thing. They're different kinds of motion. You have to worry about that. And so
I find this really hard to teach, actually, which is why I kind of appreciate you tilting at this. Use the loaf of the bread or the globe, and our natural intuitions of picturing motion in our mind has us thinking very Newtonian. Like, okay, well, the universe is a ball and it's getting bigger, and that we see this map in our head, and analogies help a little, but it kind of all breaks down, doesn't it?
So Tim, when you said that at some point the entire universe will be the local group, is that because everything else is going to be so redshifted that we're just out of sight?
That's right. It will be moved too far away for us to see, and there will be no time for the light to get to us. So if you look, say, at the Hubble constant, it's in units of, say, kilometers per second per megaparsec. And so kilometers per second is a unit of velocity, and megaparsec is a unit of distance. And so if there are a whole bunch of empty megaparsecs between you and some other galaxy group, there's a lot of room to build up a lot of kilometers per second there. But if you're looking at something that's nearby, like galaxies in our local group, they're not very far apart. And the force of gravity is powerful enough. See, I said force, even though it's not a force. Gravity is powerful enough to hold them together so they don't come apart. Whereas the gravity in that big empty space is too weak and it can't oppose the expansion. So the expansion takes place in all that empty spaces and not in the places that are full of stuff.
So then it's mostly the galaxy groups that are moving away from each other, but staying kind of stable within the group.
Yeah.
Hey, Tim.
Okay.
I think it was last decade, I heard of an idea that the reason why gravity is so much weaker than the other three forces, and that's been known for a while, is this idea that gravity exists, and maybe this is string theory talking, but gravity exists in a universe, which this universe that we're in is a subset, I guess, and that because it exists in this much bigger multidimensional universe, that's why we see it so weakly, because in this overreaching overall universe, it's powerful, but the part that we see, this four-dimensional, because time is a dimension, this four-dimensional universe, we only see a part of it, its effect. Did that ever go anywhere?
Well, that's one of the reasons for going towards multiverse cosmology, where the other forces are stuck to one universe, as it will, whereas gravity expands through all of them, and therefore, as you say, it's diluted by all these universes and looks a lot weaker. It's an idea, but so far at least, multiverse cosmology is really not easily testable. There are some cosmologists who claim that if there is a multiverse, you can see evidence for it in the cosmic microwave background, the sort of rings in the sky. Problem is that is also the same evidence you expect to see for gravitational waves generated by the Big Bang and the CMB, and that will almost certainly overwhelm anything you see from a multiverse. So it's probable that multiverse cosmology is not observationally testable in principle. So it's a theory you dive on at your last desperate need when you can't explain anything else.
Okay.
May I ask a question?
Sure.
Tim, one thing that's always bothered me about Einstein's equivalency principle is this idea that gravity, there is no measurement that could be done to differentiate gravity from an accelerating acceleration force. But if you think about it, inside that elevator or rocket ship or whatever, or sitting there in a gravitational field, there will be a gradient from your toes to your head. There's the tidal effect, which that's always swept under the carpet.
Yeah, it is. So the principle of equivalence is strictly local, which means it applies only when you're dealing with volumes of space small enough that the gravitational gradient is unimportant. So
it actually would have to be down around the Planck distance, I guess.
Yeah. So in the thought experiment, you can have an absolute, you can have a constant gravitational field. In reality, of course, you can't. And so it's a thought experiment that works as well as you can get it to work. The way we test the equivalence principle, the most popular way is to use a torsion balance experiment and look at gravitation over very small distances, like micron type distances. And if the equivalence between inertial and gravitational mass is not correct, you should see a deviation from the inverse squared attraction over those very small distances. And you might also detect compact dimensions in string theory that way. And so far, over distances on the order of 5 to 10 microns, there is no deviation from inverse square. So in principle, that means we're still safe, at least for the equivalence principle.
I think we have another question in the chat that looks pretty interesting.
There may be a whole lot of them.
Go ahead, Greg. You want to read it?
I can't pronounce the person's name because of the Cyrillic, but the question asked is, JPL needs to get away from fuel propulsion and use anti-gravity as a means for travel. Is this possible, or are there other ways around it, as it is a geometric challenge?
As far as we know, anti-gravity propulsion is simply impossible. I've never seen any way to do it. Nobody knows how to do it. There is actually a NASA laboratory that was, at least, doing research on warp drive, like Star Trek. And they've never actually been able to warp drive anything. They had some interesting results once or twice, but they get a few bucks from the NASA budget. So, but otherwise, anti-gravity, no. As far as I can tell, it's just not possible.
And then we've got Stan ask, this gets back to what we were discussing at the beginning of the QA session. Can you give an example of an observable in a physics sense, not necessarily optical sense, that can distinguish between movement through space and the expansion of space?
Probably not. I can't give an example. And the reason is all of our experiments are local, which means they're done right here where we are in our laboratory. Maybe they're done in the solar system, places where the expansion of space simply doesn't happen. And so you don't see it. The only way you can see it is by looking at something very far away. But now you're not local anymore. And so you can't pretend to know what's happening in all the space between you and that distant thing. So the expansion of the universe is, aside from your observation of galactic redshifts, the velocity is purely theoretical. If your theory for how the universe expands changes, then your interpretation of the physics changes. So, for instance, the discovery of the accelerating expansion of the universe was because astronomers used very distant type 1a supernova because they know the brightness, and they got the brightness distance, the luminosity distance, and then they got the same distance from the expansion universe theory, and they were incompatible. And so they eventually decided, well, okay, the type 1a supernova are giving us the right answer, and so our theory has to be wrong. We have to change it. That kind of observable will tell you whether your model is correct or not, but it doesn't distinguish really between motion of space versus motion through space. That's always going to be theoretical. At some point, you're just going to be stuck with that because our observations and experiments are all too local for that to work.
I have a couple of questions.
Yeah.
Ms. Martin. I'll ask what I think is the easiest one first. Can we perceive any difference in the redshift of objects that are moving through space versus ones that are moving with space?
No, and that's a problem. Because when we look, we see one redshift and only one. But that redshift is caused by the two different motions combined. One of them is the random motion through space, and the other one is the motion of space. And you have to use some theoretical assumption to break that single redshift into two different effects that you cannot distinguish observationally. And if you remember in the early days of the Hubble Key project, the groups led by Sandage and Wendy Friedman disagreed strongly over the value of the Hubble constant. And the reason they disagreed is that they used different methods for distinguishing between the movement of space and through space, and got different answers and could not come to agreement over which one is right. So no, you can't tell it.
The other kind of, I guess I've been a little suspicious that what I was taught many decades ago had not withstood the test of time, and I think you've confirmed it here, but I would just want to make sure that I'm walking away with the right understanding.
Mm-hmm.
So for a long, long time, we were taught and talked about the four fundamental forces.
Mm-hmm.
But gravity, the fourth, is not a force. Is that?
In principle, it is not a force. You could call it a force in practice, because when you hit the ground, you're going to act like it was a force. And of course, you can model gravity as a force using gravitational fields, which would give you a classical force. So you can pretend it's a force and get away with it, but in essence, it's not. It's an expression of the geometry, and you have to do it that way if you're going to try to quantize it, because a field approximation for gravity is just that. It's an approximation. You can't use that to get a quantum theory of gravity. You got to go to its native form, which is geometry.
And that was the thing where we kind of this equivalent of like a great circle through multi-dimensional space.
Yeah.
That's the geometry you're talking about.
Yeah.
And yet we talk about, or we hear, about gravitational waves being detected, which seems to imply a field, but it's really geometric, not a field. So I'm still kind of perplexed.
It is a wave of space-time, just like a wave on the ocean. The ocean doesn't go anywhere. The wave propagates through the ocean. So you have a wave of space-time, and that's what you are detecting.
So in that sense, the field is space-time.
Yeah, remember, space-time is already curved, so the gravitational wave is just imposing an extra curvature, little ripples on top of the curvature that you already have. So it's just another form of the curvature of space-time with a relatively high frequency vibration.
And that's not inconsistent with this geometric view we were
No.
talking about a minute ago.
No.
Thanks.
Mm-hmm.
Hey, Tim, I have a question about ultimate fate of the universe.
Mm-hmm. Yeah.
So I guess there are three ideas. Either it's a big rip, big crunch, or just a flat whimper. Now, the big rip is basically, it's like due to expansion of the universe, right? So is that, when you say that eventually in the far distance future, because of the expansion, all it remains is a local group of galaxies.
Mm-hmm.
But even beyond that, if it is really space is expanding, eventually, does it mean that each and every atom and molecule will rip apart and expand into just all you're left with photons? Is that comes from the expansion theory, or is that something different?
It comes from an expansion theory. The problem we have is that we are seeing a short time interval snapshot of the universe, and we make up theories to describe it. But the farther you extrapolate those theories into the future, the more questionable you get. So if you look at Einstein's equations, for instance, he has a geometry mixed in with something called a stress energy tensor, which is where you put all your normal forces, masses, energies, and all that stuff that are not geometric. And you can put the acceleration of the universe in either one of those. You can make it geometric and use the cosmological constant, or you can just skip that and put it over in the stress energy tensor and have any kind of equation you want. Problem is we don't know what the real equation is that describes, in principle, the long-term expansion of the universe. We're just looking at what we can see right now. So if you, for instance, were looking at a small enough piece of a sine wave, you might fool yourself into thinking you're seeing exponential because you're just not seeing enough of the curve. And that's where we are. We're just not seeing enough of the curve.
Wow.
So maybe if the big rip scenario is true, it'll even shred the gluons. It'll the whole everything. It'll just shred everything. But there's no way of knowing that. And maybe the real equation will have it turn around and come back. There are oscillating universe models in general relativity, in string theory, and I'm sure in loop quantum gravity. They all have theoretical constructions that allow for oscillations that will be spread out and then collapse back to a big crunch and then spread out again, expand, and then collapse back. So there's no way of knowing which one of those is right. And so you can bet your money on any of them and, take your chances.
So the cosmological constant basically doesn't really define the fate of the universe in the far distance, which is more like just what you observe right now. Explain that observation, I suppose.
We assume the cosmological constant is a constant, and we put a constant in there, but we're only able to see a relatively small chunk of the history of the universe. What if the cosmological constant is actually a cosmological function, and we haven't seen enough of the universe yet to tell the difference? Could be. So we do the best we can with the small amount of stuff that we have available to look at.
Ah, okay.
Anything else?
I've heard some people talk about the theory of dark matter, which is very much pinned on the way gravity works.
Mm-hmm.
And I guess I would invite you to comment on, does these grappling with these difficulties on what gravity is affect that? I mean, is there some truth to that argument, or is the effects that they've deduced the presence of dark matter from on solid ground?
Yeah. And so what we observe appears to be the effect of extra mass that we can't see. However, you can also explain those observations by diddling the law of gravity, maybe by changing slightly the inverse square relationship so that you don't see it over short distances, you only see it over long distances. And so there are two schools of thought in theoretical physics. One them are the people, and it's a relatively small number, but they're working away on it, trying to modify the law of gravity to explain away dark matter. So you can get rid of it altogether. And they've had some success. You can do that and look at the rotation curve of a spiral galaxy, and it works. You can get rid of dark matter altogether. But if you then take that very same theory of gravity and apply it to the motions of the galaxies in a galaxy cluster, it breaks and doesn't work. So if you fix it for the galaxy cluster and then apply it to a rotating galaxy, it breaks and doesn't work. And so they've had no real success at getting rid of dark matter altogether. On the other hand, if you just assume that what you're looking at, what you're seeing is mass or matter that you just can't see, and there's no rule that says you should be able to see everything, that's not written in the cards anywhere. If you just make that assumption, all the problems go away at once just great. You can solve the problem of galaxy clusters, galaxy rotations, star formation, dwarf galaxies, everything. You can solve all your problems at once with a mundane assumption that you have this weakly coupling dark matter. And we already know of particles that would suit that bill completely. Neutrinos would do the job. There just are not enough of them, and we know that, and so we have to look for other things. And so it's not like we're making up stuff that nobody's ever imagined before. We're just looking for stuff that's like what we already know.
Has everyone signed up for the door prizes? If not,
No, just me. So go ahead and draw.
No, I didn't sign up either.
Get busy, sign up.
So I posted the link there for everybody.
I think I signed up the instant you posted the link.
You need another hat?
Yeah, that's what I was going to ask Tim.
Yeah, I don't really need another hat.
It was really interesting, Tim. Thank you so much. I
Yeah,
really
thanks a lot.
appreciate you explaining that stuff. Clap, clap, clap.
Thank you. I thought starting with Zeno's paradox would get your attention.
Yes, very much so. I think I remember that from, when was it? Somewhere in calculus in college and series.
Oh, I liked it. No, but I liked it because there were certain details stitching together this idea and that idea that I didn't know before. So thanks a lot, Tim. Really.
You're welcome.
Yeah, I like explaining some of those, the history of understanding motion, because we all, like Diogenes, we all think we understand it perfectly, right? Throw a ball across the room, but
yeah,
when you try to make sense out of it, you know, it can
Well,
get quite
it's-
confusing.
Well, it's like all philosophy, mathematics, and science. I forgot who said it. Might have been Einstein said it. That says the tragedy of science is that you can have this beautiful theory and it's killed by one ugly fact.
Yeah, I'm afraid that happens.
Okay,
But
so
did Einstein say that?
I don't know whether he said it or not. Somebody did.
all right, I'm going to close out the drawing in about 30 seconds. They've got 50 some odd people, and only 32 have registered for the drawing. So do it now. I'm going to close it out in about 30 seconds.
The fewer people who register, the greater my chances of winning are.
Oh boy.
Yeah, another hat.
Greedy. Greedy.
All right. Okay, consider it closed.
Whoa.
All right. You can collect the Alicia, are you on?
Is
Yeah, I'm
she
here.
there she
Okay.
is.
All
How
right.
many do we have tonight, Alicia?
1, 2, 7.
7. Okay.
Good.
Well, we'll know when to stop.
Okay. Hang on a second.
All right, so Spencer will get us set up with our spreadsheet.
Yeah,
Start
hang
it
on.
off.
Hang on 1 second. I somehow lost the spreadsheet. Oh, here we go. Okay, I got it. That's what happens when you have too many windows open. Too many, that's a multiverse of spreadsheets. Okay, let's see. All
Tim,
right.
did you stop sharing?
I did.
You did. Okay, good.
Okay, I'm going to share a screen. I'm going to drop the names in here.
There we go.
You just sent me a message.
Oops, hang on just a second. Let's try this one more time.
I'm so confused. Hold on.
Okay, so Greg Thompson.
Ha!
That should have been Tim Thompson.
Oh.
Wait, what?
Is it a hat?
Outback.
You got that one, Alicia?
Hold on. I was responding to an LAS member real quick. Greg Thompson. Okay.
What did he win?
He got a LAS hat.
All right, here's the next one.
I just said
That's
Iranian.
Nady. That's Nady. Nady.
Oh, where's Nady? She here?
Yes, I'm here.
Yeah, she's there. Nady, you won something. Wait, Nady.
Finally.
You won it.
No, you scroll down before I could write her
Oh,
last.
sorry.
Oh.
Okay, you got the name. All right.
Hold on. I can't like screen grab. All right. I think I got it. Yes. I
Okay.
did.
What
And
did she
she won a red flashlight.
Oh,
All right.
All right,
Yes,
perfect.
I needed one. Thank you.
All right.
Hey,
Next one is-
excuse me, before you go on, my name is there twice. Number 2 and number 29.
Okay, so you registered twice.
I forgot.
Aha.
Cheater.
Yeah, right, Dave.
All right. So, okay, so George is.
Yay! Thank
okay.
you.
All right, so I'm going to. So I'm sorry, 2 and 29 are the same ones. Yeah. Okay. So I'm gonna delete George and delete one David, and then we'll.
What did George win? I missed that.
Okay. George won a $25 Amazon gift card.
Oh,
All
thank you.
That's always useful.
All right. So now I'm gonna hang on.
Hey,
No,
Keith.
no, hang on.
Oh,
I'm deleting there. Okay.
Oh,
wait a minute. What happened to Keith?
Because
Oh my God.
Keith might come up later, but I
You
Hadn't
won
deleted it yet.
before.
I have not won before. How dare you?
I saw the name.
But Brian's my
Wait
friend.
for
That's
you.
cool.
I'll swallow a bandage.
Brian's won before.
Maybe he'll share with you.
Brian won a Celestial Observer's map of the moon.
Hey.
Moon map. Nice one.
Yeah.
Right.
Keith, do you want a mug? Because I saw your name too, and I got confused.
Okay. All right.
No, it's actually fine. I think Brian, he won once before and he won the exact same thing.
He
And
did.
he'll just give me he can give me that one.
Okay.
Yeah.
Cool.
Okay.
That's karma. I'll take it.
All right.
You can use it at Garvey.
Okay. Phil Taylor.
Hey, Phil.
Oh, right. Phil again. Wow.
Phil. So what did you
Phil
get?
won an item from the LAS store.
All right.
Go shopping,
Okay.
Phil.
All right.
Hey, Jeff. Where is he? I saw him.
I saw him.
Yay!
There he is.
All right. Very excited.
Very cool. What do you win?
Let me just check, Jeff. You're older than 18, right? Or 21?
I
Oh,
Wait a minute, what are we giving away?
Yeah, what-
I was like, wait a minute. Okay. He won the Northern Summer Sky and Astronomy Constellation Etched 10-ounce tumblers, set of 2.
all right.
All right.
Cool.
You can always fill them with water.
Yeah,
Yeah.
exactly.
All right. And all
Hey,
right.
David.
David.
No kidding.
There you
Oh.
go.
So you
Oh,
came
wow.
up anyway, David.
He won anyway.
I'm rather embarrassed by this, but I was honest.
Yes, you were.
Thank
And
you.
Now you do get a mug.
Look, instant karma, instant reward.
What did you get,
David
Alicia?
won a Celestron I can't even speak right now. Hold on. A Celestron Skymaster 15x70 binocular.
Whoa.
All right.
Whoa, awesome.
Wow.
So
Nice.
was that 7 yet?
Yeah. Yeah.
Yes. Okay. So that was the last one.
Mhm.
All right. Okay. Well, we're done with all of our business. Everyone can stay. We can chat. We can talk more to Tim if you have any more questions. You have any questions for me?
Hey, Daryl, we had a
Okay.
question. We had a question in the chat earlier tonight about basically when are we going to do our next astro imaging class?
I saw that and responded to that person, and I've been hearing a lot about doing that from chat boards and email. So we'll start putting that together and see, when and where that can be, and who wants to do the teaching. It sounds like everyone wants to do it. We just need to organize it.
Yeah, that's exactly what I was going to say.
Well,
Yeah.
well, the thing is we've got to establish that if we demonstrate with a camera, it's going to be specifically that camera, and everybody has a different camera. It seems like to me. Maybe our best bet is to try and arrange a non-Wednesday night session at Garvey Ranch, and I'd be willing to do it. With the only problem being is I still do not have keys. Except for the power box and the observatory proper, I don't have keys.
I emailed Vance earlier today and asked him if he wanted to come to Garvey on Wednesday, that I go pick him up and take him if he's not too infirm. But that was just today. I haven't heard back from him. But one way or another, even if he can't go to Garvey, he knows that I want the keys back for you.
Do you want keys, David? When I talked to you before, you said you didn't want the responsibility. So
Yeah, but that was on the hope
Somebody
that
flipped
Vance
him.
was going to come back real soon.
Yeah.
Real soon is now real past. So I
Yeah.
think I have to just bite the bullet
Okay.
and do it.
Okay.
So just I don't know.
But
Some
if
of
the
the,
police show up, you'll know I screwed up on the code.
so there on the discussion groups, there's a new discussion group being formed. It's called Astrophotography Group, and that's came out of, I think, a result of seeing just a lot of traffic on the discussion boards about astrophotography. So there's a separate group that's being set up, and I think Dave, you're tagged as one of the moderators for that.
I haven't decided yet. Vance said he would be, but he asked me to be co-moderator, and I'm kind of leading now 60-40 in a positive direction, but 60-40 is 60-40. So I should make up my mind soon.
But anyways, I think just in watching some of the discussions that take place, there's a lot of good information that can be exchanged. Even if there's no formal moderator, I think that's probably a good place for a lot of the discussion that takes place, and not just saturate the general discussion groups. So with astrophotography specific questions or comments.
Also there's Vance Tyree's, I think, was it Vance that did the 3-part astrophotography?
Yeah,
I did
that's
one
a
part of
YouTube.
that.
Well, no, there's
on
also
our YouTube channel. There's a great 3-part astrophotography. It starts out real, on a shoestring and goes on from there into a lot of other stuff. So if you haven't done that and you're interested in astrophotography, start there, because those are just go watch it. And he's good. He's good.
Although
Yeah.
Curtis Byram commented, because I did part of that too, I did only one class, one session, and he said, "Gads, I wish there was a way to condense all that Vance said into the time space that you did it, Dave." And it's like, well, because I'm not technical, I don't go
Well,
into the technical minutia.
But there are actually two types of videos. There's one series of 3 or 4 that were done. Somebody taped or recorded an in-person session at Garvey. And I think that's the one you're probably referring to, Daryl. And so that's a very good one. That starts off, assuming that you know very little about it, starts off with basically water cameras and white polar alignment's important, things like that, and then from there it builds on. And then more recently, I think about a year and a half ago, then Dave and Vance did a series where Vance did some talk about image processing and eliminating light pollution. And Dave, that's where you did one on EasyCap.
Right. That's probably the one I was referring to. Yeah.
Yeah.
Because I only did one.
Yeah, right. Yeah, Vance did 2 on reducing eliminating light pollution in post processing.
Right.
Yeah, I
Now I
posted
remember.
in the chat, just YouTube Vance Tyree astrophotography, and those sessions come right up.
Yeah.
In YouTube. So those are very helpful, I think.
Oh, there you go.
Oh, by the way,
chat.
since the meeting's formally ended, I'm going to stop the recording.
Good idea. Thank you.
Okay.
And thank you too.